on this.
Sounds good.
Yeah, and then what I'll do is I'll post that to my YouTube channel when it processes. And you can go there. If you forget what it is, it's the Digital Math Tutor YouTube channel. If you go to YouTube and search for Digital Math Tutor,
Okay.
the recording of this session will be the first one once I get it uploaded, which can take a couple hours following the session. So don't go looking for it, you know, really right away. Yeah, it has to process it and then I have to upload it. All right. Explain how you can or cannot use the information to determine G. Well, G will do exactly the same way.
Right.
So tell me how to go. In other
Okay.
words, you always want to start there. I won't.
Perfect. Okay, so we'll
For
go.
most math problems, you want to start with the general formula.
Okay, perfect.
And what do you know here?
We know the vertex.
So tell me what to write.
So just be y equals a parentheses x minus 2, or so plus 2, right? Or no, yeah. It'd be
Oh, it is minus. The general format is x minus h.
It'd be minus 2 squared plus 1. And then
Okay.
we can go ahead and plug in another point, doing 2 equals a parentheses 2 minus 2 squared plus 1.
So solve that for a.
Okay, it'd just be 4 plus 1 is 5 minus 2. So it'd just be 3, right? Or wait, let me
Do it step by step.
Okay, so
Yeah,
we'll,
don't, a huge mistake in math is trying to do 2 steps at once.
Yeah.
Just it's open for error.
right. So we'll just do 2 equals 4 plus 1 is
For
5.
a.
For a plus 1. And then we can minus 1 and then divide by 4. So a is 1/4.
Okay. So a is 1/4.
And then we'll plug that back in. And
Let's go ahead and do it.
and
we're going to call this g of x instead of y.
G of x equals 1/4 parentheses x minus 2 squared plus 1.
Right. And that is the formula for that problem.
Correct.
Let me erase that and scroll down here. Suppose we place a new quadratic with that formula on the axis above. Explain how many points of intersection, if any, the graph of H has with the graph of F. All right. So F's the only one we care about. So I don't need to show G fully, but we want to graph that.
Okay.
So what's a good way to graph that? Because that is not in vertex format.
No.
That is in standard format.
Okay. So should we try to convert it to vertex format then?
We could do that. And it's actually not going to be that. Couple things you could do. Let's see if there's maybe an easier way to do that. Explain how many points of intersection there are. If we're looking for points of intersection, we don't really need to graph that. So all we need to do is set it equal to F.
Oh, okay.
And then solve it.
Okay. So
yeah, let's do that. X squared over 6 minus x over 3 minus 5/2 is going to be equal to
7.5.
0.7, negative 7.5.
5 parentheses x plus 3 squared plus 0.75.
Gosh, that's even makes it worse that they made us guess whether that was 0.75 or not.
Yeah.
Because if we guessed slight, in other words, if it was 0.7 instead, really changes a lot.
Right.
What's the best way to go from here?
One sec. Let me write this down on my paper as well.
We basically have one quadratic equals another. So if we can solve for x and we get only one answer, then it's going to tell us that that new parabola only intersects once. If we solve for x and we get two answers, then we know it's going to intersect twice.
Right. Okay.
So we don't really need to graph this. We just need to solve this equation. So when you're solving equations, there's two things that I like to get rid of. I like to get rid of all denominators, and then I like to get rid of all parentheses.
Okay.
So what's a good way to get rid of all denominators?
Would it be multiply everything else on the other side as well?
Multiply everything by what? What number? What single number will get rid of all three of these denominators?
It would be 12, right?
6.
6.
You don't need to go as high as 12.
Yeah,
And you want to use your smallest one.
Okay, correct.
Because if I use 12, it'll give me higher numbers across the board that I don't need. I can get rid of everything by multiplying everything by 6. So I'm going to multiply this side by 6, and I'm going to multiply this side by 6.
Right.
Apologize for not having enough room here. So let's start writing what we now have. So tell me.
1 sec, I'm writing this down.
It's actually better if you interact with me and what I'm writing.
Okay.
Rather than doing it on paper first and then transcribing that to me.
Okay, so we would start with.
It tells me how you're thinking better.
We would start with 6x squared.
Okay, hold on. That 6 cancels with that 6.
Oh yeah, my bad. Sorry. We would go with 6 times negative 0.75.
Hold on. Let's go left to right, not right to left. Start over here. Start with this 6 times this.
So that would just be x squared. And then it would be minus 6x.
2x.
Oh, 2x, right. Minus 3.
Okay, the 6 divided by 2 is 3, and you have to multiply the 3 times the numerator.
All right, so it'd just be 30 over 3.
So it's 6 divided by 2 is 3, and then 3 times 5 is 15.
All right, okay.
Never use bigger numbers than you have to.
Okay.
To put 6 times 5, that introduces 30 into the equation.
Right.
You don't want to do that ever. That's why you always, when you're doing these multiplications, you always cancel first if you can.
Sounds good.
And now over here on the other side.
Okay, so it'd be 6 times negative 0.75. So it'd just be negative 4.5.
Yeah. Now see here is if we were off a little bit, that just gets magnified.
And then parentheses 6x plus 12.
Oh, hold on. Once we've multiplied that 6 by that coefficient, we're done with this part.
Oh, okay. That makes
In other words, you don't want to multiply it by both things because these two things are being multiplied together.
Right.
So once you multiply the 6 times the minus 0.75, you're done with this part. Now we still have to multiply the 6 times the plus 0.75.
Right. So that'll just be plus 4.5.
All right. And now I think we can factor this over here. Go ahead and factor it.
It'd be x plus, or no, x minus 5, x plus 3.
And that's actually quite helpful because we have an x plus 3 over here.
Right.
That's not that helpful now that I think about it. Yeah, not that helpful at all. We don't want to really do that because then we'd have to divide this 4.5
Right.
by that. So let's back up here.
Okay.
Now let's move this 4.5 to the left.
Okay. So it'd just be 19.5. Or no, it'd just be because that's a negative 15. Or yeah, so it'd be negative 19.5.
Yeah, so okay, so let's do it like that. Now, are you allowed to use a calculator?
No.
Okay, so you could not put this into your calculator and have it tell you the answer.
No, calculators aren't allowed in this class, but
Okay, no,
on
that's
the-
fine.
on the
I'm
test,
actually glad to hear that because I think they do more damage than good. At this point, because it looks like we're not going to be able to factor this thing on the left anymore. So let's go ahead and expand this out. Now, let's get rid of parentheses.
okay,
And so what's that squared?
x plus, it'd be x squared plus 2x. Or no, sorry.
All right, you need to know how to expand a plus b squared.
So it could just be x squared.
That is always a squared plus 2ab plus b squared. So if I'm expanding x plus 3 squared, then it's going to be what?
That'd be a squared.
X squared. A is x.
Sorry, x squared plus 6a.
6x.
6. Yeah, I'm not.
It's all right.
And then plus 9.
Okay. And now we need to multiply that out. Having all of these decimals really is a pain here. You see absolutely no benefit as to why they would do that. Only makes it more difficult. And if you were able to use a calculator, it wouldn't be so bad. But we're going to have to do all of this manually.
Yeah, which is weird because they don't put like decimals usually.
No, they didn't for g of x. They only did for this f of x, which is really strange.
So negative 4.5x squared
minus 27.
27.5.
Just 27.
7.
X.
Plus or minus 40.5.
All right, now let's gather like terms.
All right, so I would plus the 2x over.
No, let's start with the left. Start with the squares, always. Always work left or right. None of this working from the inside out.
Okay.
So how many x squareds do we end up with on the left?
1.
We got minus 4.5 there. We got 1 over here. Combine them.
Okay, so it'd just be 4.5
plus 1 is 5.5.
Oh yeah, okay, 5.5x.
How many x's do we have?
It would be plus 28x is 26x.
27 minus 2.
It's hard to see the red. I thought that
Oh,
was
okay. Okay.
I thought it was a 28. So just
Yeah,
be
no, I get you. All right. And then,
plus 40.5. So
so that looks like 21.
right.
And all of that's equal to 0. Well,
There's not much we can do there.
well, we have to go to the quadratic form because they didn't make it particularly easy to try to factor. Usually when you have a coefficient in front of the x squared term that's not a whole number, you don't even try to factor it. You just immediately go to the quadratic formula, which it's hard for me to believe that that's really what they wanted you to do here, but let's do it. So starting over here on the left, what's the general formula for the quadratic?
Like what do you mean? Like the quadratic formula?
How would
or
you
what?
solve that quadratic?
Didn't you just say quadratic formula though?
Yeah, but you got to know what the quadratic formula is.
It's plus, from my memory, it's kind of hard, but plus minus.
Okay, it's minus b
Oh, okay.
plus or minus square root of b squared minus 4ac all over 2a. And this is something you want to have memorized.
Okay.
Because they don't let you look it up when they're giving you a test.
Right.
And in fact, on the SAT exam, you have to know this. They don't give it to you. So that will allow us to solve this quadratic if we merely plug it in.
Right.
Now, I don't know that it makes sense for us to go through this math. It's more important to go through the concept. Let's do the next step, and then I'll let you worry about all the arithmetic. It's kind of silly that this problem is taking up 30 minutes of our session.
Oh, I know. It's
And
crazy.
it's only because of the weird, wild numbers they gave us.
Exactly.
If what they'd have given us with g of x, I bet it would have been a whole lot simpler because g of x has no decimals or fractions in it.
Right.
And part D does ask you to compare it with G. So we're going to do this exact same thing that we did, only we're going to compare it with G. And it may be much easier to solve, but to solve it here, what's minus B? Let's just lay it out with numbers and then I'll let you take care of the rest.
That'd be minus 25 plus minus square root of 25 squared,
which is 625.
minus 4, 5.5, 21, yeah. All over 2, 5.5.
So whatever that comes out to be, and it does look like it will be 2 answers.
Okay, so it'd be 2 intersections.
Yeah, the only way that this would ever come out to be 1 only is if your discriminant were 0.
Okay.
In other words, if the part under the radical sign is equal to 0, then this plus minus goes away and you only have one answer, minus 25 over 11.
Right.
But as long as the discriminant is positive, which it is here, you're going to have 2 answers. And
Okay.
both of those are going to represent the solutions to this.
Correct.
In other words, maybe that parabola looks something like that,
Okay.
that h of x, and it's going to intersect there and there.
Right. That makes sense. Okay.
Yeah, and we didn't really need to graph it and figure out where it was, because we could have spent a lot of time doing that. And that thing isn't the easiest thing to graph.
Right.
So that would have taken a lot of time to graph it. And even then, our next step would have been this, where you just set them equal to each other to try to figure out where they intersect.
Right.
So it really would have been a waste of time to graph it.
Thanks.
Yeah, and setting one quadratic equal to the other isn't always the easiest thing to solve, as we saw here. It was actually quite difficult, and made more difficult by the fact that they forced us to guess as to what the y coordinate of f was. That's why this is kind of a horrible problem, if you want my honest opinion of it.
No, I feel like they try to make it hard on us just to like. I
Well,
don't
I know, and that's so crazy to do that. It just is. It wasted 20 minutes of time.
No, it's crazy how bad like these homeworks take. So
Okay. Yeah, unnecessarily so also, because there's just no reason. If they're trying to teach you the concept, then the concept is, if you want to know where they intersect, set one equal to the other. That's the concept.
correct. Okay.
And then they make it so that it requires a calculator to solve.
Yeah, even though we're not allowed to use.
And you're not allowed to use calculators. So something's wrong. Okay, so fill in with all, no, or some.
Okay.
All right. An example must include either a graph or a specific function. All compositions of polynomial functions f and g are polynomial functions. Now, is this still referring to the f and g that we had in problem one, or is this just some unknown f and g?
It's some unknown f and g.
Okay. So composite functions are things like this. That's a composite.
Okay.
Or
G f of x.
Yeah. In other words, whenever you take one function and you make it the argument inside the parentheses, you're going to end up with a composite function.
Right.
So the question is when you have a composite function between f and g, do you still have a polynomial for sure? What do you think?
I think it would be some, right?
The way to approach this is assume all.
Assume all.
Because we know that there are some.
Right.
In other words, if I said f was equal to x squared, and g was equal to x cubed, well, certainly fog, which is f, is this one,
yep,
is x to the sixth,
right,
which is a polynomial. So we know at least some are.
Right.
So now it's down to, we can cross that one out because we found one. So it's either some or all.
Okay.
So if we think that it's some, then we have to figure out a polynomial where it does not result in a polynomial.
Right.
And I can't. If I had something like G is not a polynomial, first of all. So if I make G any polynomial, polynomials are merely, has to have some power that's an integer, can't be a fractional. That's a polynomial.
Okay.
G equals -2 is a polynomial. Or however I combine those, I am going to get a polynomial.
Okay.
I think, hold on a second, let's see. If I made this, maybe that's not true. Yeah, and that's the way to do these is all you have to do is find one that is not a polynomial, and then we know the answer is some. So, and this might be, yeah, this is actually a good example. I did find one here. And if I took what is f of g, well, that would mean f of x squared. No, that's still x to the 6th.
X to the 6th.
I think I'm going the wrong way here. Yeah. What if I go g of f? G of f would be, yeah, that would be g of x cubed. So I'm going to plug in x cubed wherever I see x. Now I still get x to the 6th.
Yeah, so it has
So, and you don't want to get into a situation here where you have to try 10 different kinds.
right.
And see that all 10 of them result in a polynomial. In other words, if you can't figure out relatively quickly one that does not result in a polynomial, then just go with it. So at this point, since I can't find one that is not, I'm going to go with all.
Okay.
Give a brief explanation as to why. Now, I guess the explanation would be all. Oh, God. My explanation would be I tried a bunch of different combinations and all of them resulted in polynomial functions.
Okay, perfect.
Well, I don't know if that is or not, but it's not an easy thing to explain.
Right.
Polynomial functions are continuous. Is that true or false?
True.
And it's definitely true for some. In other words, if I look at a simple polynomial, that's continuous.
Right.
So certainly there is one that is continuous. Can I write a polynomial function that is not continuous is the next question. And this functions that are not continuous almost always involve division by 0 or square roots. In other words, something like 3 over x minus 2. That is not continuous because x cannot be allowed to be 0, or excuse me, 2.
Yeah, because if x is 2 and you divide by 0.
Yeah, and that violates all the laws of mathematics, divided by 0. So you know that there's going to be a vertical asymptote at x equal 2.
Right.
And this is hyperbolic in nature. So you're going to have something like this. And it's going to look like this, and that's not continuous.
Right.
But that's not a polynomial. When you're dividing by x, in other words, if you have x to the -1, that is not a polynomial.
Right.
If I put this function like right there, that's 1 over x, but it's not a polynomial. These exponents have to be positive whole integers for it to be a polynomial.
Correct.
So again, I'm going to say all.
Okay.
And again, the explanation is the same one. Couldn't find one that wasn't. Polynomial functions of degree n will have n number of real roots. True or false?
I don't know. I'm confused about that one.
Okay. Let's write a polynomial that has hold on a second. Lost my train of thought. There. That polynomial if I set this, in other words, the way you find roots is by setting f of x to 0.
So
Now, can I solve that? And the answer is no. There is only non-real roots. This is definitely a second degree polynomial, but this doesn't have any real solutions because there's no way that a number squared is equal to 0.
right.
Well, I guess it has 1 minus 3. So let's change this. Let's make this x squared plus 3. Now that has no solution. In other words, when I set f of x equal to 0 to try to find the roots, I get x squared equals minus 3, which does yield 2 solutions, but they are plus or minus root 3i. So there's 2 solutions, but neither one of them are real.
Right.
So it's definitely not true for all.
Exactly.
On the other hand, if I set that minus 3, it is true for that because now x equals plus or minus the square root of 3. And that's 2 real solutions.
Right.
So this has got to be some.
So what's with the I? Like
I is the imaginary, I is equal to the square root of minus 1.
Okay. All right.
And that you are going to get that if you haven't gotten it yet.
We have not.
Okay, yeah, that's definitely pre-calc stuff. Well, you might have gotten it in algebra 2 even towards the end. Yeah. But it's when you go to solve like quadratics and they don't have real solutions, they usually have imaginary solutions. And that's what I means is it's the imaginary number, the square root of minus 1. All right, so the next question. Odd degree polynomials have an inverse. Odd degree polynomials have an odd number of distinct real roots. And I think that is probably all. Well, let's talk about the inverse first.
Okay.
Odd degree polynomials. So let's think of one. It's the simplest one I can think of. And if I graph that one, looks like that.
Okay.
And for a function to have an inverse, it has to be 1-to-1. In other words, it has to pass a vertical line test and it has to pass a horizontal line test. Let me draw this a little bit better because the first time I drew it, it didn't pass the vertical test.
And that's because you switched the X and Y values, right?
Well, I haven't done anything yet. I
Right,
just
but-
graphed a odd
right.
degree polynomial. But it turns out that all odd degree polynomials are 1-to-1. Whereas even degree polynomials, if I look at x squared, that's a parabola.
Uh-huh.
That's not 1-to-1. It passes the vertical line test so that it is a function, but it doesn't pass the horizontal line test, meaning it does not have an inverse.
Right.
Now, if you restrict the domain of this to positive numbers only, in other words, if you say, if x is greater than or equal to 0, that restricts the domain to this part only. Now that is 1-to-1.
Mm-hmm.
So this does have an inverse, but only if you restrict the domain. And that is actually done quite a bit. They do it in trig, where they restrict the domain of sine x in order to come up with an inverse.
Mm-hmm.
Because the sine function is not 1-to-1.
Right.
In other words, it suffers from the same thing that an even polynomial suffers from. That passes the vertical line test, but it doesn't come close to passing the horizontal line test.
Right.
So they restrict the domain in order to come up with an inverse.
So it'd be all odd degree
I
polynomials.
think it's all. I've never actually tried this, trying to find out where if you had something like this, we'll make it odd. Now, even if I did that, see, now I can say that -3 equals x cubed, and that does have
Potential.
well, you can take the cube root of a negative number.
Right. Right.
So yes, you would have an inverse based on that. Now, to test all possible odd number polynomials is not really feasible to do. In other words, do I have any information that tells me that let's put an x squared in there and let's put an x in there and then let's put a number in there? Now, the question is does this have an inverse? And I'm going to say yes, it has to, because of that.
Right.
So I'm going to say all, not some.
Okay.
If I could find even one that did not,
It'd be some.
then it would be some, yeah. But I can't think of any that I know of that don't. And I'm pretty sure that all is the correct answer. And then for E, where it says an odd degree polynomial has an odd number of distinct real roots. Yeah, I believe that is also always true. The one thing about that cubic is that at most it can have 3 solutions. And it either has 3 real solutions or it has 1 real and 2 imaginary.
Okay.
And imaginary solutions always come in pairs, never one. You'll never find a polynomial that has just 1 imaginary solution.
Mm-hmm.
So it always has 2, which means that yes, it's always going to have 1 real. In other words, if I made this to the 5th, I might have 3 real and 2 imaginary, but that's still an odd number of real roots.
Right.
So I'm going to say all for that also.
Okay.
Yeah, explaining it is a whole nother. There probably is some type of mathematical proof for all of these, but there's no way they could expect you to do that.
Right.
The only real way to answer these is just go through some functions that you're familiar with and see what the answers are.
Right.
and see what happens when you try to find the roots. But I'm going to go with that. I wouldn't bet my life on all 5 of those answers, but I'd say that pretty close to. I'd bet quite a bit of money. Just wouldn't bet my life. All right. Draw a graph of the polynomial function that satisfies the following conditions. Okay, these are kind of cool. Well, if we start with a polynomial that is in standard form, like that. And now we apply these 3 conditions. Actually, there's an easier way to do it. Let's do it the easy way. Instead of putting it in standard form, let's put it into X-Intercept form. There's 3 formats for quadratics. P and Q. And this would be the X-Intercept form, where P and Q are the X-intercepts.
Right.
And if I apply this condition there, which says when X is -1, Y is -3, and then the other condition is when X is 0, Y is 0. And so does this allow me to solve for A? I think it does. Let's see, what does that become? Actually, maybe it doesn't. Yeah, actually, it, let's see, we got 0 equals APG, or APQ, excuse me. And up here, we have -3 equals, I multiply these 2 together. I get 1. Let's see, I get a plus Q and a plus P. And I get a plus PQ. I think I may have taken a wrong turn at the beginning here. A lot depends on how you start these problems off. Can I solve for A here? Well, I probably can't because I have three variables there. And I have three variables there, and I only have two equations.
Right.
So let's rethink things here. When f is -1, or when x is -1, y is -3. So that points on the graph. And that points on the graph. Draw the graph of any polynomial that satisfies that condition. Well, I can draw a straight line through that. And the polynomial that satisfies that is f of x equals, has a slope of 3, goes through the origin right there.
Right. Okay.
And I think probably with all of these, you want to use the simplest polynomial function that satisfies that.
Okay.
I could have treated this like it was part of a parabola and drew a parabola like that,
Right.
but that's more complicated. And they didn't specify how big what degree the polynomial function had to be. So you want to, for each one of these, find the simplest one. And perhaps the simplest way to do it is this way, where I just graphed those 2 points and drew a straight line through
Okay.
them. Before I let you go, let's tackle one of the harder ones here and see if we can make hide or hair on that. F of x is increasing on those 3 intervals. So from -infinity to -2, it's increasing. It's also increasing from -1 to 1. And it's also, you're familiar with the concept of increasing, decreasing, concave up, concave down?
I'm familiar with increasing and decreasing, not concave up or concave down.
These are calculus terms. That's all dependent on first and second derivatives. But let's continue on with this one. I know we're out of time, so we're not going to have time to do all of these, but we're just going to work on that one. And then it's also increasing from 2 to infinity.
All right.
So let me give you an example of a function. I will draw it that follows these 3 principles. It's got to be increasing from there to there. It's got to be increasing from there to there. It can be decreasing from there to there. It can be decreasing from there to there. There's a function.
Right.
They asked us to draw it. There you go. And that's all you really need to do. It's a mistake to try to figure out the function. In fact,
Right.
I made a mistake on the first one. I didn't need to come up with y equal 3x. So all I needed to do was plot these 2 points and connect them with a straight line. And that satisfied their request to draw a graph.
Right.
Now, in reality, you might want to smooth these out a little bit rather than make them, even though these are functions, even with the corners on them, nothing wrong with that. That can still be a function. You don't really need to smooth it out. You just have to make sure that it satisfies these 3 conditions.
Okay. Perfect.
And do the same for all of the rest.
Will do. Okay.
Okay.
So
Blake,
go ahead.
these are a little tricky, I can see, and it doesn't look like they've taught you enough yet.
No,
Because you really, this is pre-calc and it really looks like they've started calc.
Yeah, it's a pretty tough class. I'm not doing bad in it, but
Yeah,
I've been doing
but
good on the quizzes, but the reason I'm here is these homeworks right here will take me hours on end, and it's like,
have they given you limits yet?
no.
My God, well, what did they have any business talking to you about concave up and concave down until they've taught you limits?
Yeah.
Just so that you don't know,
That's
or so that you know, this is concave down. This is concave up.
Okay.
And right there in between is neither.
Okay. That makes sense.
And there's an official math definition for it, but so you know what they're talking about when they talk about concave up and concave down, this is what they're talking about.
Okay.
And this part up here is still concave up
Right.
because it still goes like that.
Okay.
Now that also violates a function, so it wouldn't do that, but maybe it would do that. And there's these points in between concavity are called inflection points.
Okay.
It's also calculus. So anyway.
All right. Well, I appreciate the extra time.
You're welcome. And good luck on this course. And I'd be happy to work with you anytime.
Yeah, I'll be scheduling them probably every Tuesday and Thursday at the same time.
Sounds good. All right, Blake.
So for billing, can you send that to my parents' email and then I'll just sign up?
Yeah, I think that's what I always used to do. I have your mom or your dad's email address.
Just send that to them and then I'll sign up with mine. So the link will go to mine.
Okay.
Okay. I appreciate it, David. Thank you.
You're welcome, Blake. Have a good one. Bye-bye.